the solution for the rather limited group is based on so-called quorums.
This is Matej Pavlovic, a PhD student of the IT school at EPFL, and in a previous video, along with Professor Rachid Guerraoui, Matej Pavlovic claimed that their recent work shows that the distributed cryptocurrency problem is actually a provably easy problem, meaning that it can be done vastly more efficiently than what's being done with current protocols like the Bitcoin protocol. Today, we'll see how, and the key idea relies on so-called quorums.
Quorum is a subgroup of the participants, such that whatever two subgroups you take, there is always at least some intersection between these subgroups. It's like in the parliament. It's also called quorums in the parliament. If you want to pass some law through the parliament, you need to convince a quorum of the parliament. For very important decisions, this quorum might be big. For regular decisions, this quorum might be just a simple majority. And a very similar principle we apply in our system.
Forget about computers for now. Let's imagine that a group of us wants to manage our own cryptocurrency with information and communication only. How would we do this using quorums?
If I want to perform a transaction that takes money from my account, I need to simply announce this intention of spending the money to enough other participants of the system. If I do this, and if I manage to convince an important part of the other participants that I want to spend this money, then I can consider this transaction as done and the money is spent.
Importantly, we need to make sure that a malicious person among us will not be able to hack our cryptocurrency system by double spending his money.
If I was a bad guy and I wanted to spend the same money in a different way, I would have to convince again a part of the system that, by the property that it's a quorum, would have to intersect with the first part that I convinced about the other transaction, and this one that is in the intersection could say, no, stop, you already spent that money.
This simple observation shows that quorums suffice to prevent double spending. So, concretely,
I tell everybody that I want to spend some money, and I wait until enough of the participants confirm to me that they are aware that I want to spend this money. In distributed computing, announcing to everybody is called broadcast, and we show that the specific way of broadcasting that we employ, which needs to still make sure that what I broadcast is consistent, that different participants do not see completely different messages from me, that this broadcast has consensus number one, and it's much easier to implement than a blockchain.
Yes, because here we only need the replies of sufficiently many machines, but in a blockchain,
if I send money to Alice and Bob sends money to Joe, everybody needs to agree which of these transactions goes first. In our system, we don't have to agree. They are completely independent as long as enough of the members know about them.
As a result,
what we can do is to implement exactly the same application as Bitcoin does, but in a much simpler and more efficient and easier way.
So, to sum up,
we can get a cryptocurrency with no proof of work, no wasting of energy, in a very efficient way.
Now, there is a big caveat to the solution we described in this video, as it
works for a limited number of participants, let's say hundreds or thousands, because for each transaction, I have to communicate with, let's say, most of them. And if I would have to communicate with 1 billion of others, that would be very expensive.
But it turns out that Matej Pavlovic and his co-authors also found a way to transform this quorum-based, highly efficient cryptocurrency protocol into a sampling-based, highly efficient and very scalable cryptocurrency protocol that should work for billions or trillions of users. But more on this another time.
We can define different classes of equivalences with k going from 1 to n. Here n is the best, 1 is the worst, and at every level of the hierarchy we can have a class of problems we can solve.
We proved that you don't need to talk with a very large number of processes. Actually, what we call samples are extremely efficient compared to quorums.